In this video, we'll talk about polarization in insulators. Now, before I start discussing how polarization takes place in an insulating object, I will start discussing how the presence of charges affects a single atom. So here I have in the picture the nucleus at the center with the electron cloud shown as yellow around the nucleus. And I have brought a positive charge near that atom. Now, I am assuming I start with an atom that is overall the center of the electron cloud overlaps exactly with the position of the nucleus. This is a non-polarized atom. Now, once I bring the positive charge near the atom, this is what happens. In materials, when you have atoms as part of an object, the nucleus is the one that is heavy compared to the electrons around it. And the nucleus is the one that tends to stay in its position. It doesn't really move. So I'm going to keep the nucleus where it is. And what will change due to the presence of that external charge is that the shape of the electron cloud will be distorted. I know that the positive charge will exert an attractive force on the electron cloud, and it will start pulling it towards its own position. So the electron cloud will be distorted, and instead of being a spherical cloud, it will be more of something that looks like this. The probability of finding the electrons is going to be a little bit greater on the side that is in between, if you want, the nucleus and the positive charge, and that's because this charge is attracting the electron cloud towards it. So if I draw a more simplistic picture of what happens, I have the charge, and with this plus I indicate the position of the nucleus, and with this minus here I'm indicating the center of the electron cloud. Now then what I can do is I can say I have a positive charge with an equal and opposite negative charge here, and they are separated by some distance s, and this is what I will call, this is what is an atomic dipole. And one thing to keep in mind in this case, when you remove this external charge, the positive charge, when you remove it, then of course the electron cloud will go back in the way that it was before. There is no polarization. This external charge induced this atomic dipole. Now, this is what happens at a single atomic level. When you bring this positive charge near a macroscopic object, for example, a block made from some insulating material, so this will be my insulating block. What I have here, I have a lot of atoms. Okay, every macroscopic object includes a huge number of atoms. And here I'm just indicating the centers of the nuclei, essentially. Now, the presence of that external charge, the presence of this, will end up inducing these atomic dipoles for every charge. See this? That's where the center of the electron cloud is. So this is the minus. How about I change the dots? This is my nucleus. It's a plus. It's a plus. Just to distinguish. And it's going to induce atomic dipoles everywhere in this insulating block. And these will be oriented on the axis that connects the external charge with the nucleus. So the orientation of the dipoles will not be the same for every one of them, but all of them will be oriented facing towards that external charge. So this will be the electron cloud, and so on. You get the idea. Every atom in this insulator will become an atomic dipole. This external charge will induce atomic dipoles everywhere in the insulating block. Now, we know, and if you remove this external charge, all of the atoms that are part of the insulating block, they will go back to the way that they were before. So one thing to keep in mind is the direction, as I mentioned, of the dipoles. The orientation will not be the same for all of them, but all of them will be facing the external charge. And also there is one more feature. Because the electric field that this charge creates depends on the distance, right? We know from Coulomb's law that the magnitude of the electric field from a single point charge falls as 1 over r squared. Then that means that the strength of the electric force that this exerts on the negative clouds, the attractive force that this charge exerts on the negative clouds, that ends up distorting the atoms, that force will also fall as 1 over r squared. This is because this means the further away you go, the less polarized the atoms are. Let's do that here. So this is going to be a smaller dipole. And now I don't have any more to show, but the further away you would go, the less polarized the atoms will be. And this is due to the distance dependence of the electric force. Now, we know that to a good approximation, okay, the dipole moment, and to remind you, when you have a dipole, when we talk about a dipole, the magnitude of the dipole moment is equal to Q times S, where Q is the charge, the positive charge, and S is the separation between the two. So let's do, this is my dipole. Okay, this is Q here, this is minus Q, and S is the separation between the two. Then Q times S will give me the magnitude of this dipole moment. Okay, every dipole has a dipole moment. Now, we know from theory, but also from experiments, that in some cases we can say that the induced dipole moment is approximately equal alpha, which we call polarizability, alpha times the electric field. And what this means is that the greater the electric field that you have at the location of the atom, the bigger the dipole that you will induce, in the case that I just described, the stronger the charge, the greater the charge that you bring here, the greater the dipole that charge will induce, which makes sense. The greater this charge is, the greater the force pulling on the electron cloud will be, and that's why you will be able to move the center of the electron cloud even further closer to that external charge, so the greater the atomic dipole that you will create. Now, the polarizability is just a factor. It can be measured experimentally, it can be calculated from quantum mechanical calculations, but at the end of the day, the important thing is that this induced dipole moment is proportional to the external electric field that you apply at the location of that atom. And you can find, I know that you can find tables with the polarizability for different atoms in books. Now, this is not okay. One thing to keep in mind: this is a linear relationship between the electric field and the dipole moment, and it's a linear because this is to the power of 1. It also implies something about the direction of the dipole moment. Since polarizability is always a positive number, what this relationship is telling us is that the induced dipole moment and this external electric field, they always point in the same direction. Now, there are cases where the dipole moment does not point in the same direction as the electric field. And for example, you may have molecules where the induced dipole moment points in a different direction than the electric field. In those cases, we will describe the phenomenon in the following way. I'm going to use matrices now. So I'm going to write dipole moment as a matrix. And this will be equal to a 3x3 matrix. That is the polarizability. I will not fill this. It will be A, X, X, and so on. Anyway, it will be a 3x3 matrix. And also, this will be the X component of the electric field. This will be the Y component, and this will be the Z component. So this is still the polarizability, but now because it's a matrix, I will call it the polarizability tensor. And with this matrix multiplication between the polarizability tensor 3x3 matrix and the electric field, this multiplication allows me to make the dipole moment point in a direction different than the direction of the electric field. For example, you may have an electric field that points this way, but once you multiply it with the 3x3 matrix, you can get a polarizability that points in a different direction. Now, this is not possible if you make polarizability to be a single number. You multiply a number, a positive number, with the vector, you get something that points in the same direction, always. Now, using though a matrix, a 3x3 matrix, to represent polarizability allows you to do exactly that. And there are in molecules, you do need to represent polarizability as a matrix.